All right, so here we go for the second part and the last part, hopefully, for chapter 9 discussions. We have conservation of momentum discussion to be start at this moment, right? So here we have two objects, 1 and 2, before they had, just before they had started interacting, they had like they were moving one from left to right, the other one was moving from right to left. When they were colliding, right, this is the duration for which these two guys have collided. And if you had to work with a time duration or delta t, right, the delta t is for the time for which these two guys are in contact after they are moving in two different directions, right? A typical collision problem, right? So they were moving from both sides, they collided for delta t time interval, and then they got detached. You have two forces, F2 on 1 and F1 on 2, right? And you have solved problems like this where we named the forces, the action-reaction forces similarly. So the impulse of ball 1 on ball 2 is the same in magnitude but opposite in direction, of course, right? Because you can see clearly that they are moving in opposite directions. Therefore, if the momentum of ball increases, ball 1 increases, the momentum of ball 2 will decrease by the same amount. And we are going to see this as a result of, we're going to see this mathematically when we are actually discussing collisions for different scenarios, okay? So a system, now here we have to actually start talking about a system and its boundary, just like the force problems. You have 1, 2, and 3, they are just interacting with each other and there is no external force. So you can call this as isolated system. And you have the environment outside this line, right? But there could be forces which are not affecting these guys. If it was a closed, if it was an open system, this is a closed system. If it was an open system, then you would have forces going in or out of the system. So there would be an interaction between the environment and the system in those cases, okay? So the total momentum of the system is conserved only if you have a closed or isolated system. If you do not consider any of the forces coming from outside, or if you don't let these objects interact with the environment, you can safely say that the total momentum of these three objects is going to, the sum of the momentums is going to be constant. It's going to be conserved no matter when you watch it. The individual momentums, of course, are going to change, but the sum of these three will not change. So external forces are forces from agents outside the system. We already talked about it, right? So if you have an open system, then it will not work, of course. But if you do have, if you don't consider, if you do have an external forces, then your net change of momentum will be equals to F net times delta t. If you do not have any external force, if you have a closed system, then these arrows do not exist, right? So your right-hand side or delta p will equal to be 0. This is a case when you have an open system. So when F net equal to 0, the total momentum is conserved. An isolated system is a system with no net external force acting on it, right? So law of conservation of momentum is very simple. The final momentum should be equal to the initial momentum, right? Or which basically tells you delta p equals to 0. The total momentum after an interaction is equal to the total momentum before an interaction. And more mathematically, this is just sum of all the final momentums, right? If you have 1, 2, 3, 4, like n number of objects, you can add the total momentum. You can find the total momentum by just adding all these individual momentums to each other. And then whatever this sum is, or whatever sum you're getting for the final momentum should be equal to all the individual initial momentums added together, okay? So, and you can do this for all the components that you know. It could be x and y, it could be like some other different coordinate axes, whatever components you have, if the momentum is conserved, the momentum is conserved along all the different axes, generally speaking, unless other conditions are mentioned. Problem solving approach. So basically what you are going to do is you are going to generate some equations. And remember, you did solve a lot of simultaneous equations in your force problems when you were trying to solve free body, like draw free body diagrams and generate simultaneous equations and solve them for unknowns. This is very similar. Here you will either know the mass or the velocity, or sometimes you would need to know the forces and stuff like that. So you are basically going to be solving problems like this, like systems of equations, and then once you have these equations solved, you will know the unknowns. Okay, so the goal is to choose a system where momentum will be conserved. So you'll have to choose a system where it is easy to work with. If you don't have an external force given to you, always work with a scenario where delta P equals to 0, and then set up equations like the final momentum all added together is equal to the initial momentum all added together. A perfect example of that is explosions, and you can see that if you have or explosion or launching or propulsion of a rocket, right? So you have a rocket. This is a system where it is a closed system because it has the rocket mass and the fuel on board. The fuel will basically explode and will generate a force or change in momentum in this direction. The change in momentum of the rocket must be in the opposite direction. So with that, it will actually propel, okay? So a lot of very simple examples could be set up using these momentum conservations, okay? Recoiling of a gun. I don't know if this is discussed, but we are going to see that as well. All right, so we can now consider all sorts of momentum conservation problems to be basically of a few types, okay? And one of them is a very interesting kind where we have like perfectly inelastic collisions. And perfectly inelastic collisions are like if you have two clay balls, right? And one is moving, and if you basically throw a second one to it, and both of these two guys stick and move in tandem, like move together, then you can call this kind of collision is inelastic. Basically speaking, when you have two objects, okay, when you have two objects and they are sticking to each other after collision, we call it inelastic collisions, okay? So not many, I think I will have to actually discuss during the class some of the subtle mathematical formula we will have to discuss about, but this is probably not all regarding collision that you should understand or know. Maybe the textbook has skipped a few slides, maybe the version that I have doesn't have a couple of slides. But anyway, what I wanted to say is that if you read the textbooks, you're going to see that there is a type of collision when two objects stick together and then move as a single object after collision. And that is called inelastic collision. And then you have a certain kind of collision where you have like two objects, just like billiard balls, you have them like bouncing from one another, right? They will basically bounce very rapidly after making a collision. And the time interval is very small. The impulse is very high. That is called elastic collisions, okay? So elastic collisions, inelastic collisions, no matter what kind of collision you deal with, you always have momentum conservation like this. The total momentum does not change. The individual momentums do change though. So this is elastic collision. The one that deals with inelastic collision would be like basically two clay balls thrown to each other, or snowballs basically. Also, they could also mimic inelastic collisions. Finally, we have to deal with some of the new topics like angular momentum. We have worked with linear momentums, right? But in this case, in here, we are going to learn about a new quantity, which is not surprisingly not a very different from what you have already learned. The linear momentum is basically mass times velocity, right? M times v. The angular momentum would just be angular mass times angular velocity. So angular mass is nothing but moment of inertia. You have already learned about it. So that's I. And then you have angular velocity, which is omega, right? So you have basically I omega as your angular momentum. Now, in order to go step by step from Newton's second law, alpha equals to tau over I, right? Tau equals to I alpha. This is Newton's second law in angular motion or rotational motion. We can say alpha equals to delta omega over delta t by definition, rate of change of angular velocity. And if you substitute delta omega over delta t over here, you are going to get tau net times delta t equals to I times delta omega, right? Multiplying each other, cross. And this is basically change of angular momentum, right? Because the linear momentum was delta p, but mass was still constant. It was just delta v. Look at here, you have moment of inertia, which is basically constant for the object until the object changes shape. And this is delta omega, right? So you can call this safely as delta L, or change of momentum. So you can say angular momentum is I omega. You can also say the angular form of the same equation, the impulse momentum theorem, could be written in for rotational motion as F net or tau net times delta t equals to delta L, right? Instead of delta p, it will be delta L. Here are some of the angular momentums that you can, here's basically a good correlation or analogous terms from rotational dynamics and linear dynamics. Force, you know that it has an equivalence in tau or torque. Mass becomes moment of inertia. Velocity becomes omega or angular velocity. Linear momentum is now angular momentum. So we are basically generating like a very similar system of parameters for rotational dynamics as we have already done for linear dynamics. And here we go. This is basically what I have been talking about, right? Law of conservation of angular momentum. When there is no net torque, then there will be no change of angular momentum. And finally, the total angular momentum is conserved just like total linear momentum. And you can write them as I1, omega 1, I2, omega 2 for all the final ones, final velocities, final angular velocities, and final moment of inertias. And also I1, omega 1, I2, omega 2 for the initial values, right? And of course, it can happen that I can change, right? You can clearly see that the initial and the final moment of inertias in these cases are taken to be different. And this can happen. You can find examples where change of shape happens because you can clearly, like, for example, if you have a disk and that's moving, that's rotating across an axis, right? You can quickly slide another disk on top of it and change the moment of inertia rapidly without stopping the motion, the rotational motion. So yes, there are examples for which you can actually see moment of inertia changing, although it's not very common. But sometimes, even if you keep the moment of inertia fixed, you can still have the angular velocity changing, and that will give you a change of momentum. So varying moment of inertia, here you can see that somebody, a ballet dancer or a snow ice skater, right, figure skater, could actually change the moment of inertia for her body, and thereby she can actually generate different kind of angular velocities, right? So of course, this is an object, this is a scenario, this is a geometry for which you have a different moment of inertia than this kind of a scenario. And these geometries play a lot of roles in order to know or to determine what kind of rotational speeds the person is going to generate. So that's basically another example of varying moment of inertia, but you can, in the lab, you can easily do this by like rotating a cylinder and then basically dropping another cylinder on top of it, or basically just putting a mass on one edge of the cylinder or a disc. It will just have a slightly different moment of inertia, and thereby the angular momentum will change. All right, so we have actually come to the very end of chapter 9. We have learned in this chapter about, especially in this segment, about collisions, about angular momentums, and how we have generated, or we can generate, a system of analogous system of angular momentums or rotational parameters for linear dynamics. And now we have like two new candidates in that list. We have a linear momentum and we have an angular momentum. And we have also established how these two guys are related to their force counterparts. All right, so I'm going to stop here, and then we are going to move again to meet again for the next chapter, which is chapter 10 discussion.